Forget the movies, forget the fiction. The real science of reaching Proxima Centauri is so much worse and so much more fascinating than anything Hollywood has ever put on a screen. Because the universe doesn't do dramatic hero moments. It does radiation, timescales that swallow civilizations whole, and silence so complete it breaks people. Are we actually built for this, or are the stars simply not meant for us? If this kind of content is your thing, make sure to give this video a like. Now let's get started. Let's talk about what deep space actually does to the human body, not the sanitized version, but the real biological data we've gathered from astronauts in low Earth orbit. Because even the relatively mild environment of the International Space Station gives us a preview that should genuinely give us pause. After just 6 months aboard the ISS, the human body begins breaking down in measurable, documented ways. Bones lose density because in microgravity they don't need to support weight, and the body is ruthlessly efficient about not maintaining structures it doesn't need. Muscles atrophy. The heart, which is itself a muscle, physically changes shape over time, becoming more spherical and less efficient at pumping blood. Fluids shift upward toward the head, creating persistent pressure that has been linked to changes in the structure of the eye and lasting visual impairment in some astronauts. Astronaut Scott Kelly spent an entire year aboard the ISS, 1 year in low Earth orbit, in a relatively well-shielded environment, with regular supply deliveries from Earth as part of NASA's twin study. Researchers compared him against his identical twin brother Mark, who stayed on Earth. The results were striking in ways scientists are still working to fully understand. Scott's gene expression had shifted, particularly in genes connected to immune response and DNA repair. His telomeres, which are the protective end caps on chromosomes that essentially function as a biological aging clock, had actually lengthened during spaceflight, which sounds counterintuitively positive until you learn they rapidly shortened again after his return, and then continued shrinking at an accelerated rate. His cognitive performance showed measurable changes. His gut microbiome was significantly altered. His carotid arteries showed early signs of thickening. 1 year, one person, one relatively nearby and relatively sheltered environment. Now scale that forward. A crewed mission to Proxima Centauri, even using the most ambitious propulsion concepts being seriously discussed in peer-reviewed science today. Concepts like nuclear pulse propulsion, where a sequence of controlled nuclear detonations drives the ship forward, or electromagnetic sail systems that use the pressure of stellar radiation and particle streams, would still take anywhere from several hundred to several thousand years. We aren't talking about one Scott Kelly anymore. We're talking about dozens of human generations born inside a metal hull, people who would live their entire lives on a ship, who would fall in love, raise children, get sick, grow old, and die, never once feeling solid ground beneath their feet, never once breathing unfiltered air. The psychological dimensions of that are something researchers have only begun to scratch the surface of. Isolation studies like the Mars 500 simulation, where 6 volunteers spent 520 days in a sealed habitat in Moscow, mimicking a round trip to Mars, revealed serious and progressive psychological strain, sleep disruptions, emotional withdrawal, reduced motivation, conflicts that grew quietly but persistently over time, and that was 520 days with people who knew Earth was right outside the door. Here's where I want you to pause and really sit with something. Everything we've talked about so far, the impossible distances, the toll on the human body, the generational weight of the journey, all of that assumes we're dealing with the hard part, but we're not. Not yet, because even if every single engineering obstacle got solved, even if someone built the perfect ship, perfect shielding, perfect life support, perfect multi-generational living spaces, perfect medical systems capable of maintaining human health across 1,000 years of transit, there is still something at the destination end of this journey that might make everything else look like a minor inconvenience. The star itself, Proxima Centauri, the quiet, unassuming little neighbor we've been dreaming about reaching, is, in the most literal and scientifically documented sense, a violent radiation-spewing, atmosphere-shredding engine of destruction. And the evidence for that comes directly from some of the most sophisticated telescopes ever constructed by human civilization. We'll get into exactly what I mean soon, because once you understand what Proxima Centauri actually does, regularly, repeatedly, as a basic feature of what it is, you will never look at that soft red dot in the night sky the same way again. And speaking of journeys through the cosmos, if you've ever wondered what it would physically feel like to travel just one single light year, not 4, just 1, I made a video on exactly that. It's on the card above. It will genuinely reshape how you experience distance. The link is on screen right now. Go watch it after this. The link is in the description and pinned on the comments. Let's talk about the star itself, because Proxima Centauri has a reputation, and it's not the kind that makes you want to move into the neighborhood. Proxima Centauri is what astronomers classify as an M-type red dwarf star. Red dwarfs are the most common type of star in the entire Milky Way galaxy, making up somewhere around 70 to 80% of all stars in our cosmic neighborhood. They burn cool and dim compared to our sun. They live extraordinarily long lives, in some cases trillions of years, far outlasting hotter, brighter stars that burn through their fuel in a cosmic blink. And for a long time, that longevity made them seem like promising candidates for hosting life. More time means more chances for complexity to emerge, right? The problem is that longevity comes packaged with something deeply unsettling, something that only became fully visible to us once we started pointing the right instruments at the right stars and actually paying attention to what we were seeing. Red dwarfs flare. They flare constantly, violently, repeatedly, and in the case of Proxima Centauri specifically, they flare in ways that make our own sun's most dramatic outbursts look like someone struck a match in a hurricane. In March of 2016, astronomers using the Everyscope telescope system, a wide-field array specifically designed to monitor stellar activity over long time periods, detected something coming from Proxima Centauri that immediately got the attention of the entire astrophysics community. It was a superflare, a single eruption of energy so enormous that it temporarily caused Proxima Centauri to brighten by a factor of 68 in ultraviolet wavelengths alone. Let me put that into context. During a typical solar flare from our sun, the increase in ultraviolet output is measured in fractions of a percent. Proxima Centauri, in a matter of minutes, became 68 times brighter in UV than its baseline. That is not a number that should sit comfortably in your mind. That particular event, documented, peer-reviewed, and published in the Astrophysical Journal, released energies estimated to be roughly 10 times more powerful than the most intense flare ever recorded from our own sun. The Carrington event of 1859, which famously disrupted telegraph systems across North America and Europe, and would, if it happened today, be estimated to cause trillions of dollars in damage to global infrastructure. That kind of event would be a quiet Tuesday by Proxima Centauri's standards. And here's where it gets worse. The 2016 superflare wasn't even the most energetic event observed from Proxima Centauri. In May of 2019, a team of researchers using the Hubble Space Telescope, alongside several other observatories operating across multiple wavelengths simultaneously, caught Proxima Centauri releasing a flare that was described in the published findings as the most powerful flare ever observed from any red dwarf in the ultraviolet spectrum. At its peak, the star brightened by a factor of approximately 14,000 in far ultraviolet wavelengths within a matter of seconds, 14,000 times brighter. In seconds, if you were standing on any surface within even a moderately close distance of Proxima Centauri when that happened, the radiation alone, before we even begin discussing the charged particle streams that follow a flare, would have been instantly lethal, not slowly harmful, not a long-term cancer risk. Instantly, comprehensively lethal to any unshielded biological organism. Now you might be thinking, all right, but these are rare events. Extraordinary stellar tantrums that happen occasionally, and with enough warning, a crew could shield themselves. That would be a deeply reasonable thing to think. It would also be wrong. Proxima Centauri doesn't reserve its fury for special occasions. Analysis of data collected over extended observation windows suggests that the star produces significant flaring events on an almost daily basis. Daily, not annually, not monthly, every single day. This star is releasing bursts of radiation and charged particles into the space around it, and superflares, events at the scale we just described, appear to occur at a rate that is, by stellar standards, alarmingly frequent. A study published in 2021, drawing on combined data from multiple space-based observatories, suggested that Proxima Centauri may produce superflares roughly a dozen times per year. Some analyses place that estimate even higher. For comparison, our Sun produces a significant flare perhaps a few times per solar cycle, which runs approximately 11 years. And an event at anywhere near superflare scale is so rare that nothing matching that category has been observed in recorded human history. This distinction matters enormously for any mission architecture involving human beings, because protecting a crew from radiation in deep space is already one of the most serious unsolved engineering challenges in human spaceflight. The primary threat isn't background cosmic radiation, although that is genuinely dangerous on its own. It's the unpredictable, sudden, high-energy particle events, solar energetic particle events, or SEEBs, which erupt in association with solar flares, can deliver lethal radiation doses in minutes if crew members aren't protected by sufficient shielding material. On the International Space Station, astronauts are partially shielded by Earth's magnetosphere, the planet's natural electromagnetic bubble that deflects a significant portion of incoming particle radiation. Beyond Earth orbit, that protection disappears. During the Apollo missions, NASA had emergency protocols in place for SEP events. Astronauts would have been directed to shelter in the most shielded part of the spacecraft and hope. Had a major solar energetic particle event occurred during one of those translunar missions, the outcome could have been catastrophic. Now take that risk and multiply it by the flaring activity of a star that erupts violently, repeatedly, every single day, for the entirety of a journey measured in centuries or millennia. This is where the telescope data becomes genuinely heartbreaking in a scientific sense, because orbiting Proxima Centauri, within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a rocky surface, there is a confirmed planet. It was announced in 2016 and confirmed through extensive follow-up observation. Researchers named it Proxima Centauri b, or Proxima b for short. It has an estimated mass of at least 1.27 times that of Earth. It orbits its star once every 11.2 Earth days. That's right. One orbit, 1 year on Proxima b, takes about 11 Earth days. For years, the existence of Proxima b generated extraordinary excitement. Here was a rocky, potentially Earth-sized world sitting in the habitable zone of our nearest stellar neighbor. If you were writing a science fiction story and needed a conveniently located planet to make the plot work, you could not have asked for better setup material. But then the radiation data started coming in, and the excitement cooled significantly. Simulations and atmospheric modeling studies published by researchers, including those at NASA's Goddard Space Flight Center, have suggested that Proxima b, if it ever had an atmosphere, has almost certainly had it progressively stripped away by the relentless flare activity of its host star. The process is called atmospheric erosion, and it happens when high-energy charged particles from stellar flares slam into a planet's upper atmosphere with enough force to blast gas molecules off into space. Over geological timescales, repeated bombardment of this kind can strip a planet's atmosphere entirely. Earth holds on to its atmosphere partly because of our magnetic field, generated by the movement of liquid iron in our planet's core, which deflects a significant fraction of incoming charged particles. Whether Proxima b has a substantial magnetic field of its own is currently unknown, but models suggest that even with a magnetosphere, the intensity of Proxima Centauri's flare output would likely still result in dramatic atmospheric loss over time. There is a study from 2017 conducted using data from the Chandra X-ray Observatory, estimating that Proxima b receives roughly 250 times more X-ray radiation than Earth receives from our Sun. During flare events, that figure spikes dramatically higher. In 2018, a team of researchers at the University of Exeter ran simulations of what Proxima b's surface conditions might look like during a superflare event. The results painted a grim picture. The surface of the planet would be bathed in ultraviolet radiation intense enough to be lethal to most known life forms, and the event would likely trigger massive chemical changes in whatever atmospheric layers remained, including the destruction of any ozone equivalent that might otherwise provide surface protection. So let's bring this back to the mission. You've built your ship. You've solved the propulsion problem somehow. You're accelerating toward Proxima Centauri at a meaningful fraction of the speed of light. The shielding on your vessel is the most advanced ever constructed, and somewhere between you and your destination, Proxima Centauri erupts. The physics of what happens next are not kind. Radiation shielding works by absorbing and deflecting incoming particles and photons. Water is actually an excellent radiation shield, dense and hydrogen-rich, which makes it effective at absorbing high-energy particles. Lead and polyethylene are also commonly considered in spacecraft shielding design. Some proposals for interstellar vessels include what are described as storm shelters, heavily reinforced compartments where crew members can retreat during high radiation events, surrounded by enough shielding material to reduce their exposure to survivable levels. But here's the compounding problem. The more shielding mass you add to a spacecraft, the heavier it becomes. The heavier it becomes, the more thrust you need to accelerate it to any meaningful speed. The more thrust you need, the more fuel you carry. The more fuel you carry, the heavier the ship gets. This feedback loop, sometimes called the Tsiolkovsky rocket equation tyranny, after the Russian mathematician Konstantin Tsiolkovsky, who formalized it in the early 1900s, is one of the fundamental constraints of spaceflight physics, and it does not bend for ambition. At interstellar scales, this problem becomes so severe that conventional chemical propulsion is rendered entirely useless. The fuel mass required to reach even a small fraction of the speed of light using chemical rockets would exceed the mass of the observable universe. That is not an exaggeration. That is what the mathematics actually produces when you run the numbers honestly. This is why researchers proposing realistic interstellar mission architectures turn to genuinely exotic physics. Nuclear fission drives, fusion propulsion, still theoretical, given that we haven't yet achieved sustained controlled nuclear fusion here on Earth. Antimatter drives, conceptually the most energy-dense propulsion system physically possible, but requiring the production and stable storage of antimatter in quantities that currently exceed our total global production by many orders of magnitude. Electromagnetic sails, laser-driven light sails. Each of these concepts has serious, substantive research behind it, and each carries its own category of engineering challenges that we are nowhere near solving at the scale required. But here's what should stay with you as we move into the next part of this journey: everything we've discussed so far, the body-destroying isolation, the multi-generational weight of the trip, the violent and unrelenting stellar fury of Proxima Centauri, all of that happens in what we might loosely call normal space, the space between here and our nearest neighbor, where at least the physics are familiar. Because once you start moving at a meaningful fraction of the speed of light, and any realistic interstellar mission would have to, the universe stops playing by the rules you grew up understanding. Time itself starts doing something strange, something that doesn't just complicate the mission, something that severs the crew from everyone and everything they've ever known in a way that is permanent, irreversible, and deeply, profoundly human in its implications. There's a moment in this story where the horror stops being about physics and engineering, where it stops being about radiation shields and fuel equations and biological decay. There's a moment where it becomes something far more intimate, far more human, and that moment arrives the instant your ship crosses a certain threshold of speed. Because at a meaningful fraction of the speed of light, and any mission to Proxima Centauri worth taking seriously would have to reach that territory, the universe quietly rewrites the rules of time itself. Not metaphorically, not poetically, literally, measurably, and with consequences that cut to the very core of what it means to be a person connected to other people. This is called time dilation, and most explanations of it stay safely in the realm of equations and thought experiments. We're not doing that today. Today we're going to make it personal. Albert Einstein's special theory of relativity, published in 1905, produced one of the most counterintuitive and thoroughly verified predictions in the history of science. Time, Einstein showed, is not a fixed constant flowing at the same rate for everyone everywhere. It is instead something flexible, something that stretches and compresses depending on how fast you are moving relative to something else. The faster you move, the slower time passes for you relative to someone who is stationary. This is not a quirk of perception. It's not an illusion created by signal delays or measurement errors. It is a genuine, physical, documented feature of how the universe works. We have confirmed it repeatedly using atomic clocks on aircraft and satellites. The GPS system you use every single day only works correctly because its satellites account for relativistic time shifts in their calculations. Without those corrections, GPS would drift by roughly 11 kilometers per day, so this isn't theoretical, this is real. Now let's talk about what it means for your crew. Say your ship reaches 10% of the speed of light, approximately 30 million kilometers per hour. That's an almost unimaginably ambitious speed by current engineering standards, but it's on the lower end of what serious interstellar mission proposals suggest would be needed. At that velocity, the time dilation effect is relatively modest but measurable. A journey to Proxima Centauri at 10% of light speed would take approximately 42 years from the perspective of someone watching from Earth. For the crew on the ship, the experienced time would be only very slightly less. The effect at this speed is small but real. Now push it. Assume some future breakthrough. Perhaps the fusion drives that researchers like those at the TAE Technologies company are actively developing, or the theoretical antimatter catalyzed pulse drives that physicists have modeled on paper, gets your ship to 50% of the speed of light. Now things get genuinely strange. At 50% of light speed, The journey to Proxima Centauri takes approximately 8.5 years as measured by clocks on Earth. But aboard the ship, time is running slower. The crew would experience roughly 7.3 years. The difference is modest at 50%, but it's already there, already creating a gap between two clocks that started synchronized and are now quietly, irreversibly diverging, pushed to 90% of light speed. Earth clocks, 4.7 years for the trip. Ship clocks, roughly 2 years. The gap is widening, plill to 99%. Earth time for the journey, 4.3 years. Ship time, just over 6 months. At 99.9% of light speed, the crew might experience only weeks or months of transit time, while years tick by on Earth. The universe is compressing experienced time for the travelers, while the rest of existence continues at its normal pace outside the hull. Now forget the equations for a moment. Forget the percentages. Let's talk about what this actually means for a real human being strapped inside that ship. You left Earth. You said goodbye to your family, your parents, your siblings, your friends, perhaps your children. You launched into the darkness knowing the journey would be long, but holding on to the idea that somewhere back home, life was continuing, people you love were breathing, growing, living. And the plan, or the hope, really, was that time would pass in roughly similar measure for all of you. But that's not what's happening. While you're moving through space at a significant fraction of light speed, time back home is running faster than time aboard your ship. Your parents are aging more quickly than you are. The friends you grew up with are growing old while you are still relatively young. By the time you reach Proxima Centauri and begin any kind of return journey, if a return journey is even part of the plan, the people you knew might be gone entirely. This isn't science fiction tragedy for dramatic effect. This is the actual physical prediction of a theory so thoroughly tested and verified that it underpins technology billions of people use every single day. And it gets lonelier still. Because even setting aside time dilation, there's the simple, brutal reality of the communication delay, light, which carries every signal, every message, every radio transmission we have ever sent into space, travels at around 300,000 kilometers per second. That is fast enough to circle the Earth more than 7 times in a single second. But at interstellar distances, even light takes years to cross the gap. A radio signal sent from Earth to a ship halfway to Proxima Centauri would take roughly 2 years to arrive. A response would take another 2 years to come back. A single exchange of messages, one question, one answer, takes 4 years. Think about the texture of human communication. Think about the conversations that matter most in a life. The ones where timing and presence and immediacy are everything. Now imagine compressing all of that into exchanges separated by years. Imagine receiving a message telling you your mother is unwell, knowing that by the time your response arrives, years will have passed. Knowing that the reality you're responding to is already ancient history from where you sit. The Mars 500 isolation study we mentioned found that psychological deterioration under prolonged isolation was one of the most consistent and serious findings, and those participants were on Earth, in a facility they knew was temporary, with real-time communication available whenever they needed it. Take away real-time communication. Add years between each message. Extend the duration from 500 days to multiple lifetimes. The psychological architecture of that experience has no precedent in human history. This is where the mathematics of biology and the mathematics of space travel collide in the most uncomfortable way. If your ship travels at speeds that make the journey last decades, even at the optimistic end of serious proposals, you are asking people to live their entire lives aboard a vessel. You are asking them to be born there, to grow up there, to fall in love there, to raise their own children there, and eventually to die there, never having set foot on any planetary surface. never having felt rain, never having seen an unobstructed horizon, never having experienced the simple biological reality of standing under an open sky. The concept of a generation ship, a vessel large enough and complex enough to sustain a self-reproducing human population across multiple generations of transit, has been seriously explored in academic literature for decades. The concept was popularized in mid-20th century science fiction, but has been examined with genuine rigor by researchers in biology, sociology, psychology, and engineering. The population genetics alone presents serious challenges. A 2018 study published in the journal Acta Astronautica attempted to calculate the minimum viable crew size for a multi-generational interstellar mission, meaning the smallest founding population that could sustain sufficient genetic diversity across multiple generations to avoid the compounding health problems associated with inbreeding. The researchers concluded that a founding crew of approximately 40 to 80 individuals would represent a dangerous minimum. More conservative estimates suggest populations of several hundred might be needed to maintain genuine long-term genetic health. But here's what the population genetics studies don't fully capture. Human societies are not just biological systems. They are cultural, political, psychological, and social structures that have always required reference points outside themselves to function. Human communities have historically defined themselves in relation to geography, to shared history, to connection with neighboring societies, to the physical reality of an environment they share with non-human life. Strip all of that away, place a group of human beings in a metal cylinder hurtling through absolute emptiness, give them no outside reference points, no horizon, no weather, no seasons, no connection to a world outside their walls except messages that take years to arrive, and then ask them to maintain social cohesion, political stability, and psychological health not for one generation, but for dozens. We have never done this. We have no data from anything remotely resembling this experience. Every isolated human community in history, Antarctic research stations, submarine crews, polar expeditions, long-duration space missions, has had one thing in common: a defined endpoint, a date when they would return to the world. Remove that endpoint, and you are in genuinely uncharted psychological territory. And this is the part of the generation ship concept that philosophers and ethicists have wrestled with most seriously, because the founders of such a mission, the people who step onto the ship voluntarily, who make a conscious choice to dedicate their lives to this journey, at least they chose, imperfectly perhaps, with incomplete information about what awaited them, almost certainly, but they chose. Their children did not choose. The second generation born aboard the ship, the third, the fourth, the 10th, none of them consented to a life defined entirely by the parameters of a vessel someone else designed, a mission someone else initiated, a destination someone else selected. They are born into a world not of their making, with no capacity to leave, no alternative path available to them, no possibility of opting out of the journey without simply ceasing to exist within the mission framework. This is not a technical problem. It cannot be solved by better engineering or more efficient life support systems. It is a genuine philosophical challenge about consent, autonomy, and the moral weight of decisions made by one generation that permanently and irrevocably shape the lives of every generation that follows. The bioethicist Konrad Socik has written extensively about this specific challenge in the context of interstellar mission planning, and his work highlights something that mission architects often prefer to bracket out and address later. You cannot design a healthy, multi-generational society from the outside. Human social systems are not machines that produce predictable outputs when given specific inputs. They are dynamic, emergent, and profoundly unpredictable over generational timescales. history on Earth offers sobering examples. Isolated communities, whether by geography, politics, or circumstance, have repeatedly developed in directions their founders could not have anticipated. Languages diverge, belief systems mutate, social hierarchies emerge in unexpected configurations. The values and priorities of the founding generation become mythology to their great-grandchildren, reinterpreted through completely different lived experiences. Now imagine that happening aboard a spacecraft. Imagine a generation born 200 years into the journey, descendants of the original crew who themselves were born aboard the ship, who have no living memory of Earth except through recordings and archives and stories passed down through generations of people who themselves had never been there. What relationship does that generation have to the mission? What obligation? What right does anyone have to demand that they continue toward a destination selected by people who died a century before they were born? Here's something that tends to get lost in the romance of interstellar travel narratives. While your crew is in transit, however long that transit takes, in whatever combination of ship time and Earth time, the universe is not waiting for you. Proxima Centauri is not a static target. Stars move. Our entire solar system is in motion relative to the galactic center, orbiting it at approximately 230 kilometers per second. Proxima Centauri has its own proper motion, its own trajectory through space relative to our Sun. Over the timescales involved in any realistic interstellar mission, this movement is not negligible. Navigation for an interstellar vessel isn't like aiming at a fixed point on a map. It requires calculating where the star will be when you arrive, not where it is now. This is a solvable navigation problem in principle, but it's a reminder that the cosmos operates on its own schedule, indifferent to the plans of the tiny biological creatures making their way through it. Proxima Centauri will continue doing what it does, flaring, burning, bombarding its orbital neighborhood with radiation, whether a mission is in progress or not, and the equipment aboard any ship making this journey faces its own relentless clock. Materials degrade, electronics fail, mechanical systems wear. Even the most robust engineering is subject to entropy, the universe's quiet, patient insistence on disorder. Maintaining every critical system aboard a spacecraft for centuries, without access to Earth's manufacturing base, supply chains, or specialist expertise is an engineering challenge that dwarfs anything in our current experience. Most people, when they picture the space between stars, picture nothing, a perfect, clean, absolute void, black and empty and silent in every direction, and that image is understandable. It's the one we've been handed by decades of films and television and casual descriptions of outer space as a vacuum. But it's wrong, not slightly wrong, fundamentally, consequentially wrong in a way that matters enormously the moment you try to move a ship through it at serious speed. The space between stars is not empty. It never has been. What fills it is called the interstellar medium, and it is a complex, dynamic, sometimes violent environment composed of gas, dust, charged particles, magnetic fields, and energetic radiation threading through everything. In the region between our solar system and Proxima Centauri specifically, the interstellar medium contains hydrogen and helium atoms, mostly hydrogen, drifting at extremely low densities. On average, there might be around 1 atom per cubic centimeter of space in this region. By any standard of comparison we use on Earth, that is extraordinarily sparse. A laboratory vacuum on Earth is far denser than interstellar space. But here is where the physics turns savage. Here is where the emptiness becomes lethal in a way that isn't immediately obvious until you do the mathematics. At low speeds, 1 hydrogen atom per cubic centimeter is irrelevant. Those atoms bounce off your spacecraft or pass right through with no meaningful consequence. But the moment your ship reaches a significant fraction of the speed of light, let's say 10%, which we already established would be around 30 million kilometers per hour. Those atoms stop being irrelevant. From the perspective of the ship, the interstellar medium transforms into something more like a particle beam. Every hydrogen atom in the ship's path is now approaching at 10% of light speed relative to the vessel. And at that velocity, each individual atom carries kinetic energy far beyond what its mass alone would suggest. The energy of a particle scales with the square of its velocity. Double the speed, quadruple the energy. Increase the speed by a factor of 10, and the energy increases by a factor of 100. At relativistic velocities, the numbers become genuinely alarming. Researchers have calculated that at 10% of light speed, the interstellar medium would subject the forward-facing surface of a spacecraft to radiation exposure, roughly equivalent to standing directly in front of a particle accelerator. At 20%, the flux of incoming particles becomes intense enough that conventional shielding materials would be progressively eroded, atoms from the ship itself being knocked away by the continuous bombardment. This isn't theoretical modeling done in isolation. The breakthrough Starshot project, the laser-propelled nanocraft initiative we touched on a while ago, has published detailed analyses of exactly this problem for their proposed probes, and the conclusion, even for centimeter-scale craft, is sobering. At 20% of light speed, the erosion from interstellar dust and gas alone would significantly damage unprotected surfaces within the first fraction of a light-year of transit. For a wafer-thin chip of silicon and circuitry, that erosion could be catastrophic long before the craft reached its destination. Now scale that problem up to a crude ship, a vessel massive enough to carry human beings, life support systems, food production, water recycling, medical facilities, and enough shielding to protect its crew from stellar radiation. That ship has an enormous cross-sectional area facing forward into the interstellar medium. Every square centimeter of that forward surface is being bombarded continuously by particles arriving at a significant fraction of light speed. The cumulative erosion over decades of transit would require either extraordinary shielding solutions or a complete rethinking of what the front of the ship looks like. Several serious proposals have suggested using a magnetic field projected ahead of the ship, a kind of artificial magnetosphere functioning similarly to Earth's own magnetic field, to deflect incoming charged particles before they can reach the hull. The concept is called a magnetic scoop or Bussard ramjet variant, depending on the specific design. Some versions of this idea also propose collecting the interstellar hydrogen as fuel, scooping it up and using it to feed a fusion drive. It's an elegant concept, and it has been seriously examined in peer-reviewed astrophysics literature since Robert Bussard first proposed it back in 1960. The problem is that subsequent analysis has revealed serious complications. The density of interstellar hydrogen is too low in most regions to make the fuel collection version viable. The energy required to compress and process the collected hydrogen would likely exceed the energy produced by burning it, and generating a magnetic field large enough and strong enough to deflect incoming particles effectively. We're talking about a field potentially spanning kilometers ahead of the ship, would itself require enormous amounts of power and infrastructure that add mass and complexity to the vessel. Every solution in interstellar mission design seems to carry this quality. You solve one problem and discover that the solution has introduced two more. The engineering challenges are not independent puzzles that can each be cracked separately and then assembled into a working whole. They are deeply interconnected, each one tugging on every other, so that the entire mission architecture has to be conceived and solved simultaneously as a unified system. No human engineering project in history has attempted anything remotely like this. And we haven't even gotten to the dust yet While individual atoms of gas are the dominant component of the interstellar medium by number, the medium also contains actual dust particles, microscopic grains of silicates, carbon compounds, and various ices ranging in size from nanometers up to perhaps a fraction of a millimeter. These grains are vastly more massive than individual atoms, and at relativistic velocities, even a dust grain, a fraction of a millimeter across, carries kinetic energy comparable to a small explosive. A 2012 paper published in the journal Acta Astronautica modeled the impact of interstellar dust grains on a spacecraft traveling at 30% of light speed. The findings suggested that even at the relatively low density of the interstellar medium, cumulative impacts from dust grains over an interstellar journey would produce craters, punctures, and structural damage to any unshielded surface that would be, over time, catastrophic. The researchers proposed using sacrificial shield layers, thick plates of material placed at the very front of the ship, designed to be gradually eroded by impacts while protecting the vital systems behind them. But even these shields would need to be replaced or regenerated over the course of a long journey, requiring either robotic maintenance systems or stockpiles of raw material that add yet more mass to an already impossibly heavy vessel. There is a concept that has been proposed in response to this called the pusher plate design, in which the forward face of the ship is essentially a massive, heavily armored impact absorber. Some nuclear pulse propulsion designs, most famously Project Orion, which was actually developed and studied seriously by the United States government in the late 1950s and early 1960s before being abandoned, incorporated similar forward armor concepts, since those ships were designed to detonate nuclear charges behind them and surf the explosion. The armor needed to survive the propulsion system was, in some design iterations, also useful for deflecting incoming debris, but Project Orion was never built, and the Nuclear Test Ban Treaty of 1963 effectively ended the practical development of nuclear pulse propulsion in any case. The physics remain intriguing, and some researchers still advocate for variants of the concept, but the engineering and political reality of detonating nuclear devices in space for propulsion has kept the idea in the theoretical column. What all of this points toward is a picture of the interstellar medium as something closer to an obstacle course than a void, a continuously hostile environment that punishes speed, the very thing your mission requires, in ways that compound with every additional kilometer per hour you try to gain. The faster you go, the harder the medium hits you back. And yet you have to go fast, because at slow speeds the journey takes longer than human civilization has existed. The universe has arranged things so that the solution to one of your problems is directly the cause of another. It's worth pausing here and acknowledging something. Everything we've discussed across these 4 sections, the impossible distance, the body-destroying radiation, the psychological devastation of multi-generational isolation, the philosophical weight of consent across generations, and now the physical hostility of the interstellar medium itself. All of this describes a journey to the nearest star, not the most distant, not the most challenging, the closest one, the one that on a map of the galaxy sits essentially on our doorstep. Proxima Centauri is 4.24 light-years away in a galaxy that is 100,000 light-years across, within a universe containing somewhere in the range of 2 trillion galaxies. When you sit with that for a moment, really sit with it, the scale of the cosmos stops being an abstract figure and becomes something felt. Something that shifts your perspective in a way that is genuinely hard to shake afterward. We are not a civilization standing on the threshold of the stars. We are a civilization standing at the bottom of a very deep well, looking up at light that has been traveling for years just to reach our eyes, wondering what it would take to reach the source. And yet, and this is the part that I find most extraordinary about this entire subject, despite all of it, despite every obstacle, every compounding impossibility, every engineering nightmare and philosophical dilemma and biological horror, despite all of that, there are human beings right now, today, dedicating their careers to solving these problems. Not because they expect success in their lifetimes, not because there is a clear path from here to there, but because the questions themselves matter. Because the act of pushing at the boundaries of the possible, of mapping the shape of the impossible, so that future generations inherit not just the dream but the detailed knowledge of what stands between them and its realization, is itself a form of progress that compounds across time. The people working on fusion propulsion, on laser sail physics, on radiation shielding materials, on closed-loop life support ecosystems, on the population genetics of multi-generational space communities, they are building the foundation, not the structure itself, but the foundation. And foundations matter even when the building is centuries away. Now, there is one more dimension to this journey that we haven't yet touched on, one that doesn't involve the ship, or the crew, or the star at the other end, one that involves something far more fundamental, something that sits at the very edge of our current scientific understanding and peers into territory where even our best theories begin to fray. What actually happens to information, to the patterns of thought, memory and identity that make a person who they are, under conditions of extreme prolonged isolation, relativistic motion, and multi-generational disconnection from the civilization that produced them? What does the human mind become after enough time in the dark between stars? And is there any science, real, peer-reviewed, empirically grounded science, that can tell us anything meaningful about that question? There is, and the answer is both more hopeful and more disturbing than you might expect. That's what we will talk about. Stay with me. If you are enjoying this video, make sure to subscribe and give a like. You'll keep getting content that makes the universe click into place in ways you didn't expect. There is a branch of science that doesn't get nearly enough attention in conversations about interstellar travel. We talk about propulsion, we talk about shielding, we talk about life support and fuel and navigation, but we almost never talk about the one system aboard any crewed vessel that is simultaneously the most essential and the most fragile, the one system we cannot back up, cannot replace, cannot reboot when it starts failing, the human mind. And I want to be precise here because this isn't a soft philosophical tangent. There is real, peer-reviewed, empirically collected data on what prolonged isolation, confinement, and disconnection from the broader world does to human cognition, identity, and psychological architecture. And when you apply that data to the conditions of an interstellar mission, what emerges is one of the most genuinely unsettling pictures in this entire conversation. Let's start with what we actually know. The most comprehensive real-world data we have on long-duration confinement comes from a combination of sources: Antarctic winter overstations, where small crews spend months in complete isolation during polar winter; submarine deployments where crews live in enclosed metal tubes beneath the ocean for months at a time with no natural light, no outdoor access, and severely limited communication with the outside world; long-duration spaceflight missions aboard the International Space Station; and dedicated isolation studies like the Mars 500 experiment and its successor programs run by the European Space Agency and Russian Institute of Biomedical Problems. What these sources consistently show is a pattern of psychological change that researchers have come to call the third quarter phenomenon. In long-duration isolated missions, regardless of the specific environment, there is a documented tendency for psychological deterioration to peak not at the beginning of the mission, when stress and novelty are highest, and not at the end, when return is imminent and motivation surges. It peaks in the third quarter, when the crew is past the halfway point, still far from the end, and the initial excitement of the mission has completely worn off, while the finish line remains frustratingly distant. During this phase, research consistently documents increased interpersonal conflict, reduced motivation, cognitive slowing, emotional withdrawal, disrupted sleep, and a measurable decline in the quality of decision-making. In submarine studies, researchers found that crew members in the third quarter of long deployments showed reaction times and cognitive performance comparable to individuals who had been awake for 24 hours straight, not because they were sleep-deprived, but because prolonged monotony and confinement produces its own form of cognitive dulling that mimics sleep deprivation in measurable ways. Now consider the third quarter of a journey to Proxima Centauri. Even at the most optimistic speeds being seriously proposed for crewed missions, you are talking about a third quarter measured in decades, potentially in generations. The third quarter phenomenon playing out not over weeks but over lifetimes, and that's before we introduce the sensory dimension. Human beings evolved in an environment of extraordinary sensory richness. We evolved under open skies that changed color across the day. We evolved with wind and rain and temperature variation, and the smell of soil, and the sound of moving water, and the sight of other animals moving through a landscape. Our nervous systems were shaped by millions of years of immersion in a complex, dynamic, endlessly varied physical world, and our psychological health, at a deep biological level, depends on that richness in ways we are only beginning to fully document. Research on sensory deprivation has shown that even brief periods of reduced sensory input can produce hallucinations, paranoia, and dissociative states in otherwise healthy individuals. The environment inside a spacecraft, even a well-designed, spacious, carefully engineered one, is by definition an environment of radical sensory poverty compared to what human neurology was built for: the same surfaces, the same sounds, the same recycled air, the same artificial lighting cycling through the same rhythms day after day, for years, for decades, for generations. Researchers studying long-duration Antarctic crews have documented a specific psychological response to this kind of monotonous environment called stimulus hunger, an intense, sometimes desperate craving for novel sensory experiences that can manifest in obsessive behavior, irrational risk-taking, and in severe cases, a kind of psychological numbing in which the individual loses the capacity to experience pleasure or motivation at baseline levels. The technical term for this state is anhedonia, and its presence in isolated crew members has been documented consistently across multiple independent studies. Some Antarctic winter-over crews have reported experiences that blur the boundary between waking consciousness and dreaming, a state sometimes called the long eye phenomenon, where individuals begin to see things that aren't there, not in the dramatic sense of full hallucinations, but in the subtler, more unsettling sense of the brain filling in sensory gaps with its own generated content. Familiar faces in shadows, movement at the edge of vision, the persistent, unshakable feeling of a presence in an empty room. These experiences emerge after months of isolation in people who are physically on Earth, with full gravity, breathable, unprocessed air, and the knowledge that spring will eventually come. Extend the timeline by orders of magnitude, remove the gravity, remove the seasonal cycle, remove any realistic prospect of return, and ask yourself what the human mind becomes under those conditions, not after months, but after years, after decades, after generations of people born into that environment, for whom it is not a deviation from normal life, but the only life they have ever known. There is a concept in psychology called environmental press, the idea that an environment exerts continuous pressure on the people within it, shaping their behavior, their values, their cognitive patterns, and ultimately their identity over time. The environment aboard a generation ship would represent the most total and comprehensive environmental press ever experienced by any human population. Every aspect of life, diet, social structure, daily routine, available sensory experience, relationship patterns, access to information, exposure to risk, all of it defined and bounded by the parameters of the vessel. What kind of people does that environment produce across multiple generations? We genuinely do not know. There is no precedent. There is no data. There is educated speculation grounded in evolutionary psychology and anthropology, but nothing that rises to the level of empirical certainty. Some researchers are cautiously optimistic. They point to the extraordinary human capacity for adaptation, the way our species has thrived in environments as radically different as Arctic tundra and equatorial rainforest, high-altitude plateaus and desert landscapes. They argue that human beings are fundamentally flexible, that culture and community can sustain psychological health under almost any physical conditions, and that given enough time, people adapt to whatever environment they inhabit and come to experience it as normal. Others are considerably less sanguine. They point to the documented outcomes of isolated human communities throughout history, communities cut off from broader society by geography, conflict, or circumstance, and note that the results have frequently been negative in ways that compound over time. Genetic bottlenecks, loss of accumulated knowledge, breakdown of institutional structures, emergence of rigid hierarchies, or conversely, of social fragmentation that makes collective decision-making impossible. The historical record of isolated human communities is not, on balance, an encouraging one. And there is a third perspective, one that I find both the most intellectually honest and the most philosophically challenging. It comes from researchers who argue that the very concept of maintaining a continuous human identity and mission purpose across multiple generations is fundamentally incoherent. That identity, purpose, and meaning are not stable properties that can be packaged up and transmitted intact from one generation to the next, like a file copied between computers. They are living, dynamic constructions that each individual and each generation rebuilds from scratch using the materials available to them. The founders of the mission understood why they were going. They felt it. It was connected to their lived experience of Earth, their knowledge of human history, their direct relationship with the civilization that launched them. Their grandchildren, born aboard the ship, will have access to recordings and archives and educational materials describing all of that, but they will not feel it the same way, cannot feel it the same way, any more than you feel the urgency of events that happened 500 years before your birth, the same way the people who lived through them felt it. What happens when a generation decides, somewhere in the middle of the journey, that they don't want to continue, that the mission their ancestors committed to is not their mission, that they would rather turn back or stop and simply live where they are, in the ship, rather than press on toward a destination that none of them have ever seen and none of them will live to reach? There is no mission control that can override that decision at interstellar distances. There is no authority outside the ship. There is no recourse. This is not a hypothetical designed to be dramatic. It is a genuine governance problem that researchers in the field of interstellar mission planning have identified and discussed seriously in academic literature. And there is no consensus answer. Because there may not be one, the physicist and author Gregory Benford, who has written both science fiction and serious academic work on interstellar mission planning, has described the generation ship governance problem as potentially the most difficult challenge of the entire endeavor, more difficult than the propulsion problem, more difficult than the radiation shielding problem, more difficult even than the navigation problem, because the engineering problems, however formidable, exist in a domain where progress is at least theoretically measurable. You can test a shield, you can measure thrust, you can calculate a trajectory. You cannot run a controlled experiment on the multi-generational social dynamics of a sealed human community traveling between stars. There is no prototype, there is no test flight. The first attempt will be the only attempt, and if it goes wrong in ways that couldn't be anticipated, the consequences are borne entirely by the people inside the hull. And yet, here is the thing that keeps this from being purely a story of impossibility. Here is the part that, if you sit with it honestly, shifts the emotional register of everything we've been discussing. Every single generation of human beings that has ever lived has inherited a world they didn't choose, defined by decisions made before their birth, shaped by forces entirely outside their control. Every child born into every civilization throughout history came into existence within constraints they had no say in, into languages they didn't select, into belief systems, social structures, technological realities, and environmental conditions they inherited rather than chose. The generation ship makes this explicit and extreme in ways that force us to confront it directly, but the underlying condition of being born into a world already in motion, already defined, already committed to a trajectory is not unique to space travel. It is the universal condition of being human. We are all, in a sense, passengers on a ship we didn't design, heading toward a destination our ancestors chose, carrying forward a mission most of us never explicitly agreed to. The generation ship just makes the metaphor uncomfortably literal. There is something in that parallel, something that connects the terror of the interstellar journey to the deepest questions of what it means to live a meaningful life inside constraints you cannot escape. What it means to find purpose and connection in a bounded world. What it means to be human in the fullest sense of that word, when the universe around you offers no guarantee of safety, no promise of arrival, and no map of what you'll find when you get there. We are made of stardust. Every atom in your body was forged inside a star that lived and died before our sun was born. You are, in the most literal chemical sense, a child of the cosmos, and Proxima Centauri, that violent, radiation-drenched, small and furious red star, is made of the same stuff you are, different arrangement, different circumstances, but the same fundamental materials, shaped by the same fundamental forces, part of the same 4-billion-year-old story that began with a big bang and is still being written right now, in your neurons, in the heart of that red dwarf, in the mind of every person who has ever looked up at the night sky and felt something they couldn't quite name. That feeling has a name. It's called wonder. And it's the reason, the only reason that ultimately makes sense. Why human beings keep asking the impossible questions. Keep pointing telescopes at distant stars. Keep running the mathematics of journeys they know they will never take. Because the questions themselves are worth asking. Because curiosity is its own reward, independent of whether it leads anywhere we can reach. There's a question that almost never gets asked in conversations about interstellar travel, not because it's unimportant, it might actually be the most important question of all. It gets skipped because it's uncomfortable in a way that's different from the engineering discomfort of unsolved propulsion problems or the biological discomfort of radiation exposure. It's uncomfortable because it reaches into something we tend to protect, our sense of what we are, our assumption that the thing doing the traveling and the thing that arrives at the other end will be recognizably the same. The question is this: if a journey to Proxima Centauri takes long enough, measured in generations, in centuries, in the slow accumulation of experiences and adaptations and evolutionary pressures that no human population has ever encountered before, Does the crew that arrives still qualify as human in any meaningful sense? And if the answer is no, or even maybe, what does that do to every justification we've ever offered for making the trip? This isn't philosophy for its own sake. There is real science here, and it starts with something called directed evolution, or more precisely, with the question of what happens to a species when a small, isolated subpopulation is separated from the main population and subjected to a radically different environment for a sufficiently long period of time. We know what happens. Evolution has shown us, repeatedly and across thousands of species, what isolation and environmental pressure do to a population over time. They change it, sometimes slowly, sometimes remarkably quickly by geological standards. The isolated population diverges from the original. Genetic drift, the random fluctuation of gene frequencies in a small population, begins reshaping the gene pool in ways that have nothing to do with adaptation and everything to do with chance. Mutations that would be diluted into irrelevance in a large population become fixed in a small one simply through the mathematics of random inheritance and, simultaneously, the specific pressures of the new environment, the gravity, the radiation levels, the diet, the light cycles, the disease environment, the social structure, begin selecting for traits that improve survival and reproduction within that specific context. In the context of a generation ship, this process would begin operating the moment the founding population separated from Earth. The ship environment would immediately begin exerting its own selective pressures. Individuals who cope better psychologically with confinement and monotony, individuals whose bodies handle microgravity or reduced gravity more efficiently, individuals whose immune systems adapt more effectively to the specific microbial ecosystem of the ship. Over generations, these advantages would translate into differential reproductive success, the raw material of evolution. A 2018 study published in the International Journal of Astrobiology modeled the potential rate of genetic divergence for a generation ship crew over a multi-century voyage. The researchers found that even under conservative assumptions about population size and reproductive patterns, the crew's genetic profile would show measurable divergence from Earth baseline humans within roughly 3 to 4 generations. Over 10 to 20 generations, a span well within the transit time of any realistic interstellar mission, the divergence could become substantial. Substantial doesn't necessarily mean dramatic in physical appearance. Evolution doesn't work on Hollywood timescales, but it does mean real, measurable differences in physiology, disease susceptibility, metabolic function, and potentially neurological architecture. The ship's descendants might process sensory information differently, might have different baseline stress responses, different circadian rhythms shaped by artificial light cycles rather than solar ones, different immune profiles shaped by the specific microbial environment of a sealed vessel rather than the vast and varied microbial world of an open planetary surface. And that's before we consider the intentional side of this equation, because here is a conversation that is happening right now in serious academic and bioethics circles. If you're sending human beings on a journey that will span multiple generations, and you have the technological capability to intervene in the genome of the founding population, or of subsequent generations born aboard the ship, is there not a compelling argument for doing exactly that, for deliberately engineering traits that make the crew better suited to the specific demands of the mission? Enhanced radiation resistance, more efficient oxygen metabolism suited to recycled air systems, reduced caloric requirements to ease the burden on food production systems, improved psychological resilience to isolation and monotony, greater cognitive flexibility, longer lifespan, enhanced immune function. Each of these modifications taken individually sounds like a straightforwardly good idea. Each one makes the crew more likely to survive the journey and arrive at the destination capable of establishing a viable presence. And the technology to pursue these modifications, CRISPR-based gene editing, epigenetic programming, synthetic biology, is advancing at a rate that means these capabilities, while not yet available at the sophistication required, are not obviously beyond the reach of the coming centuries. But the moment you begin deliberately altering the human genome for the purposes of an interstellar mission, you have crossed a line that raises questions which don't have clean answers. Who decides which traits are enhanced? Who decides what counts as an improvement versus a loss? Who has the authority to make irreversible genetic decisions for every generation that will be born from that modified founding population? And perhaps most fundamentally, at what point does a population that has been intentionally redesigned for a specific environment stop being human in the sense that launched the mission in the first place? This question has been examined with genuine seriousness by researchers including Cameron Smith at Portland State University, who has published extensively on the population genetics and bioethical dimensions of interstellar colonization. His work consistently highlights what he calls the identity continuity problem, the difficulty of maintaining a coherent answer to the question of what we are trying to preserve and propagate when the act of preservation itself requires modification. There is a version of this argument that leads somewhere extraordinary. If we're willing to modify the crew to suit the journey, why stop at incremental biological adjustments? Why not go further? Why not consider sending not biological humans at all, but something derived from us, something that carries our knowledge, our values, our accumulated culture and scientific understanding, but packaged in a form better suited to the demands of interstellar travel? This is where the conversation about artificial intelligence and whole brain emulation enters the interstellar travel discussion. And it's a conversation that serious researchers are having with serious intent. The concept of mind uploading, scanning the complete neural architecture of a human brain and running it as a software simulation on a substrate that isn't biological, remains firmly in the theoretical column. We are nowhere near achieving it. The human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses whose precise configuration encodes everything that makes a person who they are. Mapping that structure at sufficient resolution to reproduce it faithfully is a challenge that makes the engineering problems of interstellar propulsion look modest by comparison. But the concept is not physically prohibited. There is no law of nature that says the pattern of information that constitutes a mind cannot in principle be instantiated in a non-biological medium. And if you could preserve the consciousness, the memories, the personality, the accumulated knowledge of a human being in a form that doesn't require food, doesn't age, doesn't need breathable air or liquid water or protection from radiation in the same way biological tissue does, the calculus of interstellar travel changes completely. A digital mind running on sufficiently robust hardware could in principle make the journey to Proxima Centauri at whatever speed the ship can achieve without experiencing the passage of time at all between departure and arrival, simply powered down for transit and reactivated at the destination. No psychological deterioration from isolation, no biological decay from radiation, no multi-generational governance crisis, no question of consent across generations, because there are no generations. The same minds that set out from Earth would wake up at Proxima Centauri. The philosopher and futurist Nick Bostrom has written extensively about the implications of this concept, and his work highlights both the extraordinary promise and the profound philosophical pitfalls. because the question of whether a digital copy of a mind is the same person as the biological original or a different person who merely shares their memories is not a question with a clear scientific answer. It touches on the deepest and most contested problems in philosophy of mind, problems about the nature of consciousness and subjective experience that remain genuinely unresolved despite centuries of serious thought. If you copy your mind into a digital substrate and send that copy to Proxima Centauri, is the thing that wakes up at the destination you, or is it a replica of you? Something that believes it is you, that has all your memories and experiences and personality traits, but that came into existence at the moment of copying while the original you continued living and eventually dying on Earth. These are not idle philosophical games. If mind uploading ever becomes technologically viable, they become the most urgent practical questions in the ethics of space exploration. And here's what makes this entire dimension of the discussion so remarkable in the context of our specific journey. Proxima Centauri, as we've established, is an extraordinarily hostile environment. Its radiation output alone makes the surface of any planet in its system deeply problematic for biological life as we know it. But for a sufficiently robust digital intelligence running on radiation-hardened hardware, the calculus is different, meaningfully different. The thing that makes the destination inhospitable for beings like us might not be nearly as problematic for beings like us, but different. Beings that emerged from human intelligence but are no longer constrained by human biology. The astrobiologist David Grinspoon, in his book Earth in Human Hands, makes an observation that I think cuts to the heart of all of this. He suggests that the distinction between biological and artificial intelligence may ultimately be less important than the distinction between intelligence that is curious, creative, and committed to understanding the universe and intelligence that is not. By that measure, a digital mind that carries forward human curiosity, human wonder, human commitment to exploration and understanding is more genuinely human in the ways that matter than a biological organism that has lost those qualities. It's a perspective that both comforts and unsettles me every time I encounter it, because it suggests that what we're really trying to send to Proxima Centauri, what the mission is ultimately about, beneath all the engineering and the biology and the physics, is not a body, not a genome, not even a specific pattern of neurons. It's a quality of attention, a way of engaging with the unknown, a disposition toward the cosmos that says, whatever you are, however vast and indifferent and dangerous, we are here, we are paying attention, and we want to understand you. That quality, that orientation toward wonder and inquiry, is genuinely the most precious thing our species has produced. And the question of how to carry it across 4.24 light-years of violent, empty, radiation-drenched space, in whatever vessel or substrate proves capable of surviving the journey, is in some ways the deepest question that interstellar travel raises. Not how do we get there, but what do we mean by we, and what do we hope to find when the answer to that question looks back at us from the other side of the journey, because there is something waiting at Proxima Centauri that we haven't discussed yet. Something that the most recent telescope observations have revealed about this system that changes the emotional texture of everything we've been exploring. Something that makes the destination not just scientifically fascinating, but personally, almost unbearably significant. In 2021, researchers using the European Southern Observatory's espresso spectrograph confirmed something that the astrophysics community had been circling for several years with a mixture of excitement and careful caution. There is a second candidate planet in the Proxima Centauri system. Designated Proxima Centauri d, it orbits even closer to the star than Proxima b, completing one orbit in just under 6 Earth days. It is estimated to be less than a quarter of Earth's mass, making it one of the lightest exoplanets ever detected. And in 2022, additional data suggested the possible presence of a third body in the system, though that candidate remains under investigation and has not been definitively confirmed as of the most recent published literature. A system, not a star with a single questionable planet, a system with multiple worlds, potentially including bodies in or near the habitable zone around the star closest to our own. Whatever horror the journey represents, and we've spent considerable time mapping that horror honestly and in detail, the destination is not nothing. It is not an empty endpoint justified only by its proximity. It is a place, a complex multi-bodied system around a star that has been burning for billions of years, a star that despite its violence has had time, enormous, almost incomprehensible time in which, on at least one of its worlds, something might have found a way, that possibility. And it is a possibility, not a certainty, and I want to be precise about that, is what the next part is about. The real science of what we know and what we genuinely don't know about the potential for life in a system being continuously bombarded by its own star. And the answer is considerably more nuanced than you might expect. Let's talk about life. Not life as a philosophical abstraction or a science fiction premise, but life as a scientific possibility, one that researchers are examining with real instruments, real data, and a level of rigor that has increased dramatically over the past decade as our detection capabilities have grown more sophisticated. Because the question of whether anything lives or could live in the Proxima Centauri system is not one that serious scientists dismiss. It's one they are actively, carefully, and with genuine uncertainty investigating. And to understand where that investigation currently stands, we need to start with something that permanently changed how scientists think about life's resilience. Something discovered not in a telescope observation or a theoretical model, but in the most inhospitable corners of our own planet. For most of scientific history, life was understood to require a fairly specific set of conditions: moderate temperatures, liquid water, stable chemistry, protection from radiation, a relatively calm and predictable environment. This assumption shaped everything from the design of early exoplanet surveys to the definition of the habitable zone itself. That ring around a star where conditions seemed hospitable enough for life as we understood it. Then we started looking more carefully at Earth, and what we found in place after place was life where it had absolutely no business being. Organisms called extremophiles, a broad category covering dozens of distinct biological strategies for surviving conditions that would kill most life forms, have been found thriving in environments that systematically violate every assumption about what life requires. Thermophiles living in hydrothermal vents at the ocean floor, at temperatures exceeding 100 degrees Celsius, under pressures that would crush a human being instantly. Psychrophiles metabolizing and reproducing in Antarctic ice at temperatures far below freezing. Halophiles flourishing in the Dead Sea, one of the saltiest bodies of water on Earth, at salt concentrations so high that most organisms would be osmotically destroyed within minutes. Acidophiles living in highly acidic mine drainage environments. Alkaliphiles thriving at pH levels that would denature most proteins, and most relevant to our discussion of Proxima Centauri, radio-resistant organisms. Life that can not only survive but actively function under radiation levels that would be lethal to humans many times over. The most famous example is Deinococcus radiodurans, sometimes nicknamed Conan the Bacterium in scientific circles, a nickname that tells you a great deal about the affection researchers feel for this particular organism. It can survive radiation doses of up to 1.5 million rads, roughly 3,000 times the dose that would kill a human being. It accomplishes this through an extraordinary efficient DNA repair mechanism that can reassemble a completely shattered genome from hundreds of fragments in a matter of hours. It has been found living inside nuclear reactors. It has survived exposure to the vacuum of space in low Earth orbit experiments. It is, by any reasonable measure, one of the most radiation-tolerant organisms ever discovered. Deinococcus radiodurans is not an alien. It evolved here, on Earth, under conditions that were comparatively mild. Its extraordinary radiation resistance is thought to have evolved initially as a response to desiccation, extreme drying, which causes similar types of DNA damage to radiation exposure. The radiation resistance came along as a kind of biological side effect, which suggests something genuinely profound. Radiation resistance at extraordinary levels is not an exotic adaptation requiring specific cosmic conditions. It's something that can emerge through ordinary evolutionary processes, driven by entirely different selective pressures, and end up conferring capabilities that extend far beyond the original context. What does this mean for Proxima Centauri b, or the other candidate bodies in that system? It means that the radiation environment of Proxima Centauri, as severe as it demonstrably is, does not constitute a definitive argument against life. It constitutes an argument against life as we currently experience it, living on the surface of a planet with a robust atmosphere and magnetosphere that together filter out the vast majority of incoming radiation before it reaches us. Life in the open, on an exposed surface, under the full fury of a flaring red dwarf, would face extraordinary challenges. Life underground, however, life in subsurface rock, in liquid water trapped beneath a frozen surface layer, in hydrothermal systems heated by geological activity deep below any planetary crust, is a completely different conversation. The subsurface of a planet is shielded from stellar radiation by the rock above it. Kilometers of rock provide radiation shielding that no spacecraft engineer has to worry about designing, because geology provides it automatically, and we know from direct evidence here on Earth that life penetrates deep into the subsurface. The deep biosphere, as it's called, extends kilometers below Earth's surface into rock formations that have been isolated from the surface environment for millions of years. Organisms in these environments don't depend on sunlight. They derive energy from chemical reactions between rock and water, a process called chemolithotrophy, which is as ancient and fundamental as metabolism gets. A 2017 study led by researchers at Johns Hopkins University estimated that the total biomass of life in Earth's deep subsurface might actually rival or even exceed the total biomass of all life on the surface. The surface biosphere, every forest, every ocean, every creature you have ever seen, might represent only half or less of all living matter on this planet. The other half is down there, in the rock, in the dark, quietly metabolizing at timescales so slow that a single generation spans what would be centuries by our biological clock. Now place that understanding next to Proxima Centauri b, a world that has been bombarded by stellar radiation for billions of years, a world that may have had its surface atmosphere progressively stripped away, a world where the surface under a flaring red dwarf is a genuinely brutal environment for any organism operating there in the open, but a world that also has, in all likelihood, a rocky interior, geological heat generated by radioactive decay and tidal forces, the possibility of liquid water maintained underground by geothermal energy, independent of any surface temperature or atmospheric condition, the possibility of chemical gradients between rock and water that could drive a metabolism. We cannot confirm any of this. Let me be absolutely clear about that. We have no direct evidence of life in the Proxima Centauri system. We don't even have direct atmospheric measurements of Proxima b. The planet's orbital geometry doesn't currently favor the transit observations that allow telescopes like the James Webb Space Telescope to analyze an exoplanet's atmosphere as starlight filters through it. Proxima B's orbit, as best we can determine, doesn't transit the face of its star from our line of sight, which means the atmospheric spectroscopy techniques that are revolutionizing exoplanet science elsewhere are not currently applicable to it. The James Webb Space Telescope, which has already transformed our understanding of exoplanet atmospheres for planets around other stars, detecting carbon dioxide, water vapor, methane, and sulfur dioxide in the atmospheres of worlds dozens and hundreds of light years away, cannot yet give us that data for Proxima b. This is one of the most frustrating specific limitations in current observational astronomy, and researchers are actively exploring what alternative detection strategies might be applicable. But here's what the Webb telescope and its predecessors have taught us that is directly relevant. Life, when it exists, tends to leave chemical signatures in the atmosphere of its planet. The simultaneous presence of oxygen and methane, gases that react with each other and would rapidly deplete without continuous replenishment, is considered a strong potential biosignature because the most plausible replenishment mechanism is biological activity. The presence of nitrous oxide in quantities that can't be explained by known abiotic chemistry is another candidate biosignature that researchers have begun taking seriously. And ozone, which forms from oxygen produced by photosynthetic life, has been proposed as a detectable proxy for biological oxygen production even when direct oxygen detection is difficult. None of these signatures have been detected from Proxima b because we don't yet have the atmospheric data to look for them, but the fact that we now have instruments capable of detecting them from worlds dozens of light years away represents a revolution in our search capability that would have seemed like science fiction just 2 decades ago. The gap between where we are and where we need to be to answer the life question for Proxima b is real, but it is closing, and there is another angle to this that tends to get overlooked. Even if Proxima b itself turns out to be lifeless, stripped of atmosphere, bombarded beyond recovery, geologically dead, the existence of additional bodies in the Proxima Centauri system opens new possibilities. The confirmed candidate Proxima d, orbiting even closer to the star, is too close to be in any conventional habitable zone, but further out in the cooler, calmer orbital territory that might exist beyond the intense radiation zones near the star, the possibility of additional undetected bodies hasn't been ruled out. Proxima Centauri's low luminosity means that its habitable zone sits very close in, but it also means that the star's gravitational influence extends outward into a region where additional bodies could in principle exist and remain gravitationally stable. The search for those bodies is ongoing. Radial velocity measurements, astrometric observations, and the continued analysis of archival telescope data are all being applied to refine our picture of the Proxima Centauri system. Every new observation adds a pixel to an image we are only beginning to see clearly. There's something I want to sit with for a moment here, because it matters to how we emotionally relate to all of this. We have established, across the preceding parts of this video, that the journey to Proxima Centauri is among the most challenging undertakings imaginable, that it would demand solutions to problems we don't currently know how to solve, at scales we can barely conceive of, across timelines that dwarf all of recorded human history. We've looked honestly at what that journey would do to the body, to the mind, to the social fabric of any crew attempting it, and to the very definition of what we mean by human. And now we're sitting here acknowledging that at the other end of all that, at the destination that costs so much to reach, there might be nothing. A dead, radiation-scorched, atmosphereless rock orbiting a violent star, a monument to what happens when geological bad luck places a planet too close to a star that doesn't know how to be gentle. Or there might be something, not necessarily something that waves back, not necessarily anything complex enough to be recognized immediately as alive by eyes trained on life as we know it here, but something, some chemistry happening in some dark subsurface environment that represents the universe's second attempt in this tiny corner of one galaxy among 2 trillion at the improbable experiment of self-replicating matter, some pattern that persists, that maintains itself against entropy, that uses energy to stay organized in defiance of the universe's default preference for disorder. Even the simplest, most primitive, most alien possible version of that would be the most significant discovery in the entire history of our species. Without qualification, without competition, nothing we have ever found, built, written, or understood would come close to the implications of finding even a single-celled organism living in the rock beneath the surface of Proxima b, because it would mean that life is not a fluke, not a one-time accident that happened on one pale blue dot in one unremarkable corner of one galaxy. It would mean that given the right raw materials and enough time, the universe tends toward life, that the chemistry of self-replication is not a cosmic lottery win, but something closer to an inevitability, a deep pattern woven into the fabric of physical reality that emerges whenever and wherever conditions permit. And if life is not a fluke, if it's a pattern, then the universe is almost certainly teeming with it, in numbers so large they defy the kind of intuitive comprehension that even the distance to Proxima Centauri resists. The implications of that realization cascade outward in every direction simultaneously and don't stop. That's why people spend their careers on this. That's why the question of what lives in the Proxima Centauri system, unanswered, perhaps unanswerable with current technology, perhaps requiring a journey we have not yet figured out how to make, is worth every hour of intellectual effort invested in it. Because the answer, whatever it turns out to be, reshapes everything, and we are, right now, closer to being able to answer it than we have ever been. Not close in the sense of imminent, but close in the sense of trajectory. We are moving toward the answer. The instruments are getting sharper. The models are getting more sophisticated. The community of researchers working on these questions is growing, and the questions themselves are getting better, more specific, more empirically grounded, more connected to things we can actually measure. But here's where the next dimension of this story opens up. Because even as we grapple with what might be at Proxima Centauri, even as we weigh the horror of the journey against the magnitude of what might be waiting, there is a parallel conversation happening in the scientific community that reframes the entire premise. A conversation about whether the journey to Proxima Centauri, in anything like the form we've been imagining, is even the right question to be asking. What if the most important step toward Proxima Centauri isn't a ship at all? What if it's something we build here in this solar system, long before anyone or anything departs? What if the real prerequisite for reaching our nearest stellar neighbor is a type of civilization we haven't become yet? And what if becoming that kind of civilization is itself the most extraordinary journey in the story? If you are still with me, this channel was made exactly for you. Don't forget to subscribe and give this video a like. Every day we go somewhere the imagination barely reaches and come back with real answers. There is a framework in theoretical physics and futurism that doesn't get nearly enough attention outside of academic circles, despite the fact that it might be the single most useful lens through which to understand humanity's current relationship with interstellar travel. It was proposed in 1964 by the Soviet astronomer Nikolai Kardashev, and it goes by the straightforward name of the Kardashev scale. You may have encountered it in passing, but I want to go somewhere with it that most explanations don't reach, because when you apply it honestly to our current situation, it produces a realization that is simultaneously humbling And, in a strange way, deeply motivating, Kardashev proposed classifying civilizations by their energy consumption, specifically by the total amount of energy they are capable of harvesting and using. A Type 1 civilization, by his definition, is one that has mastered the full energy resources of its home planet, capturing all the solar energy falling on its surface, all the geothermal energy rising from its interior, all the kinetic energy of its wind and water and tidal systems, and can deploy that energy in a controlled, directed way for any purpose it chooses. A Type 2 civilization has expanded its energy mastery to encompass its entire star, harvesting the full output of its sun through structures like a Dyson sphere or Dyson swarm, arrays of energy collectors placed in orbit around the star to intercept its radiation before it dissipates into space. A Type 3 civilization commands the energy resources of an entire galaxy. Each step up the scale represents not just a quantitative increase in energy, but a qualitative transformation in what a civilization can do and where it can go. The gap between Type 1 and Type 2 is vast. The gap between Type 2 and Type 3 is almost incomprehensible, and the gap between where we currently sit and Type 1 is, in its own quiet way, both clarifying and sobering. We are not a Type 1 civilization, not even close. The physicist Michio Kaku has estimated that humanity currently sits at roughly 0.73 on the Kardashev scale, a fractional designation that Kardashev himself didn't originally include, but that researchers have added to accommodate civilizations in transition toward Type 1 status. We harvest a tiny fraction of the energy our sun delivers to Earth. We burn fossil fuels at enormous cost to the planetary systems that sustain us. Our energy infrastructure is fragmented, inefficient, politically contested, and nowhere near unified into anything that could be described as planetary-scale mastery. A Type 2 civilization, one that has built the infrastructure to harness the full output of its star, would have access to energy resources roughly 10 billion times greater than what we currently command. 10 billion times. With that energy budget, the engineering problems of interstellar travel don't disappear, but they transform from impossible to merely extraordinarily difficult. The fuel requirements that make chemical rockets useless at interstellar scales become trivial when you have a star's worth of power to draw from. The shielding requirements that force painful mass trade-offs in conventional spacecraft design become manageable when mass and manufacturing capacity are effectively unlimited. And here is the connection that tends to get lost. The journey to Proxima Centauri, done properly, done in a way that gives whatever we send there a real chance of arriving intact and capable, almost certainly requires a Type 2 civilization to execute it. Not because of any single engineering challenge, but because of the cumulative demand across all of them simultaneously. The propulsion system needs to be orders of magnitude more powerful than anything we currently have. The shielding needs to be comprehensive and self-maintaining over centuries. The life support or mind preservation system needs to be essentially perfect over timescales that have never been attempted. The communication infrastructure needs to function across light years for decades or centuries. The navigation needs to account for the proper motion of a stellar target across transit timescales measured in generations. No individual piece of that list is obviously impossible for a sufficiently advanced civilization, but assembling all of it simultaneously at the scale required, while also maintaining the political will and institutional continuity to keep a centuries-long mission on course. That is the kind of undertaking that requires not just advanced technology, but a fundamentally different relationship between a civilization and its long-term goals. And this reframing matters enormously, because it shifts the conversation from where are our interstellar ships to what kind of civilization do we need to become, and how do we get there from here. The second question has a much clearer set of near-term answers than the first. It points toward things we can actually do now, decarbonizing our energy systems, developing fusion power, and progress on this front has been real and accelerating, with the National Ignition Facility at Lawrence Livermore National Laboratory achieving fusion ignition, a reaction that produced more energy than the laser energy delivered to the target. In December of 2022, a genuine milestone that made headlines around the world, expanding our presence in the solar system to develop the resource base and manufacturing capacity that interstellar mission architecture ultimately requires, protecting and extending the institutional and scientific infrastructure that makes sustained multi-generational research programs possible. These are not small tasks, but they are tasks with traction. Tasks where effort produces measurable progress, where each step builds on the last, where the trajectory, however long, points in the right direction. There is a concept that the astronomer and science communicator Carl Sagan wrote about with characteristic precision and feeling, which he called the cosmic perspective. The idea that seeing ourselves honestly, seeing our civilization for what it currently is, a young and volatile species on a small planet with extraordinary potential and equally extraordinary capacity for self-destruction, is not a source of despair but of orientation. It tells us where we are. And knowing where you are is the prerequisite for navigating toward where you want to go. Where we want to go ultimately is out there, among the stars, to Proxima Centauri and beyond, to the hundreds of billions of other stellar systems in this galaxy alone, each with its own planets, its own chemistry, its own 4-billion-year story that has been unfolding in the dark, unseen, waiting for something curious enough to come and look. But the path to out there runs through here first. Through becoming the kind of civilization that deserves the stars, not in a moral sense, as though the cosmos grades on character, because it doesn't. In a practical sense, the kind of civilization with the wisdom to manage the timescales involved, the patience to sustain effort across generations, the ethical maturity to grapple honestly with questions about consent and identity and what we mean by us, and the technological capability to actually make the journey survivable. We are not that civilization yet, but we are, arguably, the first generation in human history that can see clearly enough to understand what becoming that civilization requires. The first generation with the scientific framework to map the obstacles honestly. The first generation with instruments sensitive enough to detect planets around nearby stars, to measure their atmospheres, to ask the life question with tools that might actually produce an answer. The first generation to have launched probes that have left the solar system entirely, Voyager 1, currently more than 23 billion kilometers from the Sun, still transmitting, still measured, still teaching us things about the heliospheric boundary and the interstellar medium that no model had fully predicted. That is not nothing. That is the beginning of something whose scale we can barely perceive from inside it. And there is something else happening right now that is directly, practically relevant to the Proxima Centauri question. Something that doesn't involve crewed ships or generation vessels or any of the long-time alien challenges we've spent the last several parts examining. It involves the laser propulsion concept from breakthrough Starshot that we introduced in Part 1, but I want to go deeper into it now, because the current state of that research is more nuanced and more interesting than the headline version usually conveys. The Breakthrough Starshot initiative, announced publicly in 2016 with backing from Yuri Milner and the late Stephen Hawking among others, proposed using a ground-based laser array estimated to require somewhere in the range of 100 gigawatts of combined power to accelerate gram-scale light-sail probes to approximately 20% of the speed of light. At that velocity, a probe could reach Proxima Centauri in roughly 20 to 25 years and would fly through the system for a brief window during which its onboard instruments could capture images and data before continuing outward into space. The engineering challenges for breakthrough Starshot are formidable and well documented within the project's own published research. The laser array required doesn't exist and would represent an infrastructure investment vastly exceeding anything in current human technological experience. The light sail material needs to reflect essentially all of the laser energy directed at it. Absorbing even a small fraction would vaporize it. The onboard electronics need to survive the acceleration phase, which would subject the probe to forces of roughly 60,000 times the gravitational acceleration at Earth's surface for a period of several minutes. And then there's the interstellar medium problem we explored in Part 4. Even a gram-scale probe traveling at 20% of light speed accumulates significant erosion damage from gas and dust impacts over a 20-year journey. Each of these problems has research groups actively working on it. Materials scientists studying candidate light sail substances, photonics engineers developing the laser coherence and beam focusing technologies required to keep a concentrated laser aimed at a centimeter-scale target for the minutes of acceleration. Radiation hardening specialist designing electronics capable of surviving both the acceleration phase and 2 decades of cosmic ray bombardment in transit. The project's Scientific Advisory Committee, which includes some of the most distinguished names in contemporary astrophysics and engineering, has consistently described these challenges as difficult but not physically prohibited. There is no law of nature being violated by any component of the Starshot concept. The obstacles are engineering obstacles, which means they exist in a domain where human ingenuity has repeatedly surprised itself. If a Starshot probe or something like it were to successfully reach the Proxima Centauri system, even if it could only capture data during a brief flyby before continuing outward, the scientific return would be extraordinary. Direct imaging of the planet candidates at resolutions no Earth-based or near-Earth telescope can achieve. Atmospheric sampling data, magnetic field measurements, radiation environment characterization, a direct look at what is actually there, rather than the indirect inferences we currently rely on. And here's the timeline that should make this feel immediate rather than abstract. If research and development on the breakthrough Starshot concept proceeds at an optimistic but not unrealistic pace, a probe launch might be feasible within several decades, putting it well within the lifetime of people alive today. The probe's 20 to 25-year transit would bring it to the Proxima Centauri system sometime in the second half of this century or the early part of the next. The data it returns, traveling back toward Earth at the speed of light, taking 4.24 years to arrive, could reach us before the end of the 22nd century. That's not a guarantee. It's not even a probability estimate because the engineering uncertainties are too large for confident probability assignment. But it is a genuine possibility, a reachable point on a trajectory that exists in the same physical reality we inhabit. Not a dream deferred to an unspecified future, an actual project with actual people working on it right now, today in real laboratories with real funding. And even if breakthrough Starshot specifically doesn't pan out, even if the laser array proves economically impossible, or the light sail material proves physically inadequate, the research it generates feeds forward into every subsequent approach. Every problem solved, every material characterized, every physical limit mapped more precisely becomes part of the knowledge base that the next attempt draws from. Science doesn't fail in the way that individual projects fail. Science accumulates. Each attempt, successful or not, adds to the foundation that makes the next attempt more informed. This is the rhythm of the entire enterprise when you step back far enough to see it. Centuries of astronomy building to the point where we could identify stars close enough to consider reaching. Decades of rocketry building to the point where we could leave our planet entirely. Years of exoplanet science building to the point where we could confirm worlds around nearby stars and begin asking questions about their atmospheres. And now, at this precise moment in history, a generation of researchers standing at the edge of a new phase, one in which the question of reaching another star stops being purely theoretical and begins acquiring the texture of an engineering problem, still enormously difficult, still requiring solutions we don't have, but increasingly, specifically, tractably difficult in ways that earlier generations couldn't even frame clearly enough to begin attacking. We are the generation that gets to frame the question properly. That is not a small thing, and it connects back to something I want you to carry forward from this video. Not just the horror, though the horror is real and worth confronting honestly. Not just the wonder, though the wonder is equally real and equally worth sitting with. But the combination of both, the honest acknowledgement that the universe is vast and indifferent and dangerous, and that we are small and fragile and brief, held together with the equally honest acknowledgement that we are the part of the universe that knows this about itself, that looks outward and feels the scale and asks the questions and builds the instruments and does the mathematic. That combination, humility and ambition, wonder and rigor, terror and curiosity held together in the same breath, is what science actually is at its best. And nowhere is that combination more alive than in the question of Proxima Centauri. There is a moment that happens to almost everyone who spends serious time with cosmology, not a gradual realization that builds slowly over years of study, but an actual moment, sudden, disorienting, and permanent in the way that genuine perspective shifts always are. A moment where the scale of the universe stops being a collection of imprem equals numbers and becomes something felt, something that lands in the chest rather than the head, and once it lands there, it doesn't leave. For some people, it happens looking through a telescope for the first time and understanding that the smear of light they're seeing isn't a star but a galaxy. 100 billion stars, each one potentially hosting worlds, all of it compressed by distance into something that fits inside the field of view of a backyard instrument. For others, it happens reading about the cosmic microwave background, the faint afterglow of the Big Bang itself, permeating the entire universe, detectable in every direction simultaneously, a fossil of the moment everything began. For others still, it happens somewhere quieter, in a parking lot late at night, staring up, suddenly and viscerally aware that the darkness between the stars is not empty darkness but depth, incomprehensible, unnavigable, genuine depth, stretching outward in every direction without an edge. Whatever triggers it, the experience shares a common structure. First, a kind of vertigo, a destabilization of the ordinary sense of scale that governs daily life, where a long drive feels like a significant distance, and a tall building feels like an impressive height. Then, following the vertigo, something unexpected, not despair, which would be the logical response to the realization of one's own cosmic insignificance. Something closer to its opposite, a strange, specific, almost inexplicable sense of privilege, of being extraordinarily lucky to be the kind of thing that can have this experience at all. That feeling has a name in psychology. The researcher Dacha Keltner at the University of California, Berkeley, has spent years studying the emotion scientifically, and he calls it awe. Awe, in its technical definition, is the response to encountering something that is simultaneously vast, beyond your current mental frameworks to fully contain, and requires what Keltner calls accommodation, a restructuring of how you understand the world in order to make room for what you've just encountered. The cosmos, honestly confronted, produces awe in almost everyone who confronts it honestly. And Keltner's research has documented that awe, reliably and measurably, makes people more curious, more generous, more collaborative, more connected to others, and more willing to think beyond their immediate self-interest toward larger frames of time and community. Awe, in other words, is not just an emotional response. It is a cognitive and social resource, and the cosmos is the most reliable awe-generating phenomenon available to our species, accessible to anyone willing to look up on a clear night and let the scale of what they're seeing actually register. I'm telling you this because it connects directly to something I think is the most important thing to understand about the Proxima Centauri question. Not the physics of it, though the physics matter enormously. Not the engineering of it, though the engineering is where the rubber meets the road, but the psychological and civilizational function of it. The reason why the question exerts such a persistent gravitational pull on the human imagination, generation after generation, culture after culture, long before we had any realistic prospect of answering it. We are drawn to Proxima Centauri and to the stars generally because the drive to explore, to push beyond the known boundary and see what lies on the other side, is not a luxury or an eccentricity of a particular subset of unusually adventurous individuals. It is, as best as evolutionary biologists and anthropologists can determine, a core feature of what our species is. It is woven into us at a level that predates civilization, predates language, predates every social institution we have built. The same impulse that drove the first anatomically modern humans out of Africa and across every habitable landmass on this planet, across land bridges and open ocean, into Arctic cold and equatorial heat, into every ecological niche a sufficiently resourceful primate could occupy. That same impulse is alive in everyone who has ever looked at Proxima Centauri and thought, what if it's not rational in the narrow sense of that word? The cost-benefit analysis of interstellar exploration, done purely in terms of immediate material return, does not obviously justify the investment. The resources required are staggering. The timescales involved exceed any normal institutional planning horizon by orders of magnitude. The probability of return on investment within any individual human lifetime, or any political cycle, or even any currently existing civilization's lifespan is not high, and yet the history of exploration suggests that this narrow cost-benefit framing consistently fails to capture what exploration actually produces. The voyages of the Polynesian navigators who crossed the Pacific in outrigger canoes, navigating by stars and ocean swells across thousands of kilometers of open water, with no maps and no guarantee of finding land. Evaluated purely on material terms, these were wildly expensive, extremely dangerous endeavors with deeply uncertain payoffs, but they populated an ocean. They built cultures and knowledge systems and navigational sciences that represented some of the most sophisticated practical astronomy in human history. They demonstrated, repeatedly, that the human capacity to solve problems expands to meet the scale of the challenge undertaken. The same pattern runs through every major chapter of human exploration. The payoffs are never quite what was expected, because expectation is bounded by existing knowledge and existing frameworks, and the most important discoveries are by definition the ones that lie outside those frameworks. The things you find that you weren't looking for, the questions that didn't exist until the journey created the conditions for asking them. And here is the thing about Proxima Centauri, specifically, that I think gets lost in the horror of the journey's difficulty. Everything we have learned in the process of taking this question seriously, everything generated by the research programs, telescope observations, mission planning exercises, bioethical debates, population genetic studies, atmospheric modeling projects, and laser propulsion experiments we've discussed across this entire video, all of it has produced knowledge and capability and conceptual frameworks that extend far beyond the specific question of interstellar travel. The research on radiation shielding has applications for cancer treatment. The research on closed-loop life support has applications for sustainable agriculture and water systems on Earth. The research on long-duration human psychological health has applications for healthcare, prison reform, submarine design, pandemic isolation management, and the treatment of conditions from depression to dementia. The fundamental physics research that underpins every aspect of the propulsion question has historically been the seedbed of technologies whose applications nobody predicted at the time. Science aimed at the stars has always returned value to Earth, not because that was the plan, but because genuine inquiry, pursued honestly and rigorously at the frontier of what is known, generates understanding that propagates outward in every direction. The same intellectual culture that produced the mathematics of orbital mechanics also produced the mathematics of financial modeling. The same engineering tradition that built the Saturn V rocket also built the microprocessors that run the device you're watching this on. Asking the Proxima Centauri question seriously, not as a thought experiment, but as a genuine engineering and scientific challenge, makes us smarter, more capable, and more connected to each other across the institutional and disciplinary boundaries that normally keep researchers isolated in their own domains. Astrophysicists have to talk to biologists, who have to talk to materials scientists, who have to talk to psychologists, who have to talk to philosophers, who have to talk to ethicists, who have to talk to engineers. That conversation is itself enormously valuable, independent of whether it ever produces a ship, but I also want to be honest about something that the wonder and the inspiration shouldn't be allowed to obscure. Because this video has been about the horrifying reality of the journey, and the horror deserves to be respected, not dissolved into uplift. The honest answer to the question of whether we will ever send human beings to Proxima Centauri is, we don't know, not we don't know yet, implying confident eventual success. Simply, we don't know. The obstacles are real. Some of them may prove insurmountable at the level of biological human travel specifically. The universe is not obligated to be traversable by creatures with our particular physiology, our particular psychology, our particular social needs. It may simply be the case that the distances involved are too great, the hazards too severe, and the timescales too long for the kind of beings we currently are to successfully bridge them in crude form. That possibility should be held alongside the wonder, not hidden behind it. Honesty about the difficulty is not pessimism. It's the thing that makes the ambition meaningful. Anyone can aspire to something easy. Aspiring honestly to something genuinely difficult, something that might not be achievable at all in the form originally imagined, that might require us to become fundamentally different kinds of beings in the process of attempting it. That's something else. That's the deepest expression of what our species is capable of when it's operating at its best. Carl Sagan wrote, in his book Pale Blue Dot, that exploration is not a choice for our species, it is an imperative. That we are by nature wanderers, that the planet we were born on is, in the cosmic scheme of things, a mote of dust suspended in a sunbeam, and that the vastness surrounding it calls to us in a way that we cannot fully explain and cannot ultimately resist. He was right about the calling. He was right about the impracticality of resisting it, but I think the calling is even richer than the wandering metaphor fully captures. We are not just wanderers, we are understanders. What drives us toward the stars is not only the instinct to move and explore and claim new territory, it is the need to comprehend, the need to know what is out there, what the universe is made of, how it works. whether the chemistry of life that produced us here has expressed itself elsewhere, in other forms, under other stars, in other oceans and rock formations, on other worlds we have never seen. The need to know where we fit in the cosmic story, not as the protagonists at the center of a human-scale drama, but as one expression among potentially countless expressions of the universe's remarkable tendency to produce complexity, consciousness, and curiosity from the raw materials of hydrogen, time, and physics. That need, the need to understand, is what makes us look at a small, dim, violent red star 4.24 light-years away and feel something complicated, something that contains terror and wonder and ambition and humility all at once, something that refuses to resolve into either confident optimism or comfortable resignation, something that insists on staying open, staying curious, staying honest about the difficulty while refusing to accept the difficulty as a final answer. That insistence is the most human thing I know. More human than any particular technology or cultural artifact or historical achievement. The refusal to stop asking. The commitment to sitting with a question that may not be answerable in your lifetime or in the lifetime of your civilization as currently constituted, and treating that question with the seriousness and care it deserves anyway, because the question is real. The star is real, the distance is real, and somewhere in that distance something is happening that we don't yet understand, and the not yet understanding is the beginning of everything. You are made of the same atoms as Proxima Centauri, not metaphorically, literally. The carbon in your body, the oxygen in your lungs, the calcium in your bones, the iron in your blood, every heavy element in your body was forged inside a star that lived and died before our solar system formed. You are, in the most rigorous chemical sense, a product of stellar evolution, a temporary arrangement of star stuff that has achieved the improbable property of being able to look back at the stars and wonder about them, to measure them, to calculate their distances and compositions and ages and planetary systems and radiation environments, to feel afraid of them and drawn to them simultaneously. That is what you are. That is what we are. And the fact that Proxima Centauri is difficult, genuinely, perhaps prohibitively difficult, doesn't change what it means that we're asking the question. It deepens it. Let's come back to Earth for a moment. Literally, because there's something grounding that needs to happen before we close this out. Something that pulls all of these threads, the distance, the radiation, the biology, the psychology, the philosophy, the life question, the civilization question, into a single coherent picture. Not a tidy picture, the universe doesn't do tidy, but a true one. Right now, tonight, if the sky is clear where you are, you can go outside and look in the direction of the constellation Centaurus. You won't be able to see Proxima Centauri with the naked eye. It's far too dim, a magnitude 11.1 star that requires a decent telescope to resolve from the background darkness. But you can look in the right direction. You can orient your body toward it and know, with the full weight of everything we've discussed, what lies along that line of sight. 4.24 light-years of interstellar medium, gas and dust and cosmic rays and magnetic fields threading through what looks to the eye like nothing, and at the end of that nothing, a small, furious, ancient red star, circled by at least 2 confirmed candidate worlds, burning with a violence that makes our own sun look sedate, and doing all of this quietly, continuously, indifferent to the fact that on a pale blue dot, orbiting a different star, a species of curious primates has spent decades pointing instruments at it and asking what it is. That gap between you standing in your backyard and that dim red star is the most honest measure of where we are right now, not as a source of despair, as a coordinate, a GPS reading for our civilization's current position in the larger journey. We are here, the star is there. The distance between those 2 points is not fixed in any meaningful sense. It is not an immutable property of reality that will remain constant regardless of what we do. It is a challenge, a specific, measurable, scientifically characterizable challenge that has a shape we can map, and therefore, in principle, a solution we can approach. We are approaching it. Slowly by any impatient measure, but genuinely, measurably, with increasing sophistication and increasing precision. Every year that passes adds to our understanding of what Proxima Centauri actually is, its flare behavior, its planetary system, the radiation environment experienced by its worlds, the composition of the space between it and us. Every generation of telescope technology gives us sharper eyes. Every advance in propulsion physics, in materials science, in our understanding of human biology in extreme environments, every one of these moves us incrementally but genuinely toward the point where the journey from here to there stops being impossible and becomes merely extraordinarily difficult. And I want to say something about the timescale of that trajectory, because I think our instinctive impatience, which is itself a deeply human and in many ways admirable trait, can distort our relationship with long-horizon progress in ways that do us a disservice. Consider what has happened in the last 100 years. A century ago, we had not yet broken the sound barrier. We had no electronic computers. We had no knowledge of DNA. No understanding of quantum mechanics at a practical level, no concept of the cosmic microwave background, no confirmed knowledge that galaxies other than our own existed. The entire framework of modern cosmology, the Big Bang, cosmic inflation, dark matter, dark energy, the accelerating expansion of the universe, all of it was either unknown or in its earliest, most tentative theoretical infancy. The idea of detecting planets around other stars was not even a serious scientific aspiration. It was speculation 1 century. And from that starting point, we have gone to the moon, sent probes to every planet in our solar system and beyond, confirmed thousands of exoplanets, sequenced the human genome, built global communication networks, achieved fusion ignition in a laboratory, and developed telescope technology capable of detecting atmospheric chemistry on worlds dozens of light years away. 1 century did that. Not 10 centuries, not a millennium, one. Now consider the next century, and the one after that, and the one after that. Not with the specifics predicted. Predictions about technological trajectories have a poor historical track record, because the most important developments are by definition the ones nobody saw coming, but simply with the recognition that the rate of accumulation of scientific understanding and engineering capability has been, across the modern era, extraordinary by any historical measure, and there is no obvious physical reason why that accumulation should stop. A civilization that in 200 years has achieved controlled fusion power, established a permanent industrial presence in the solar system, developed genuine closed-loop biological life support capable of sustaining communities indefinitely, and made meaningful progress on either biological adaptation or mind preservation technologies, that civilization is in a completely different relationship with the Proxima Centauri question than we are today, not necessarily ready to launch, but genuinely, substantively closer in ways that are hard to fully conceptualize from where we currently stand. And in 300 years? In 500? We genuinely cannot know, which is itself one of the most exciting things about being alive at this particular moment in the story. We are early, not discouragingly early, but interestingly early. The early chapters of something whose later chapters will be written by people who don't exist yet, using knowledge that hasn't been discovered yet, with capabilities we cannot currently imagine. And what we do right now, the questions we take seriously, the research we fund, the young scientists we inspire, the cultural value we place on curiosity and exploration and honest inquiry, directly shapes the foundation those future chapters are built on. There is a concept in long-term thinking called cathedral thinking, named after the medieval cathedrals of Europe, most of which took longer to build than a single human lifetime. The craftsmen who laid the foundation stones of Notre Dame de Paris, begun in 1163, knew they would not live to see it completed. The architects who designed the flying buttresses that would be added over the following century were designing solutions to engineering problems for a building that wouldn't fully exist until generations after their deaths. And yet they built, carefully, with extraordinary skill and attention to detail, because they understood that they were participants in something larger than any individual life, and that the quality of their contribution would determine the quality of what those future hands would have to work with. Interstellar exploration is cathedral thinking at its most extreme. The foundation stones are being laid right now, by the researchers at Breakthrough Starshot refining their laser array calculations, by the bioethicists wrestling with the consent problem for generation ships, by the population geneticists calculating minimum viable crew sizes, by the materials scientists developing radiation-hardened electronics, by the atmospheric scientists modeling what biosignatures might look like on a world orbiting a red dwarf, by the teachers who will inspire the students who will become the researchers who will make the discoveries that nobody currently knows need to be made. You are part of this, not as a passive observer of a story unfolding at a comfortable distance, as an actual participant, because science, real science, the kind that moves civilizations, is not a closed system accessible only to credentialed professionals. It is a culture, a set of values and habits of mind and ways of engaging with the unknown that exists in everyone who approaches a question with genuine curiosity and refuses to accept an answer that doesn't hold up to scrutiny. Every person who watches a video like this one and actually thinks about it, who lets the scale land, who sits with the difficulty honestly, who feels the wonder without using it to paper over the genuine uncertainty. Every one of those people is participating in the culture that makes progress possible. Curiosity is not passive, it is generative. It produces conversations and questions and connections between ideas that wouldn't exist without it. It creates the social permission for scientific ambition, the broad cultural recognition that these questions matter, that the resources and attention and institutional support invested in answering them are justified, that the journey itself has value even when the destination remains out of reach. Science doesn't thrive in a vacuum of public indifference. It thrives when the culture it's embedded in shares its values, when people care about the answers, when the questions feel important, not just to specialists, but to anyone with eyes to look up and a mind willing to sit with what they see. So here is what I want to leave you with. Not a summary, because everything we've covered deserves to sit in your mind as a whole, not as a list of bullet points. Not a conclusion, because the question of Proxima Centauri is definitionally open, and anyone who offers you a conclusion is selling you something that the science doesn't support. But an orientation, a way of holding everything we've discussed as you walk back out into the ordinary world after this video ends. The journey to Proxima Centauri is real, the obstacles are real, the horror is real, and I used that word deliberately in the title of this video because I think sanitized versions of this story do a disservice to the genuine scale of the challenge. The radiation is real, the distance is real, the biological toll is real, the psychological devastation of multi-generational isolation is real. The philosophical impossibility of transmitting consent and purpose and identity across centuries is real. None of that is exaggerated for effect. All of it is drawn from peer-reviewed science produced by careful researchers using real instruments. And simultaneously, with equal weight, held in the same breath, the wonder is real. The fact that we know all of this is real. The fact that we have built instruments sensitive enough to detect a planet around a star 4.24 light-years away, a planet we cannot directly image, whose existence we infer from the tiny gravitational wobble it induces in its parent star, a wobble measured in meters per second from a distance of 40 trillion kilometers, that is real. The fact that there are human beings right now, today, seriously and rigorously working on every component of the problem we've mapped across these 10 parts of this video, that is real. The fact that you, right now, know more about the honest difficulty and the genuine wonder of this question than the vast majority of people who have ever lived, that is real. And that knowledge is not a burden, it's an inheritance. One of the most extraordinary ones our civilization currently has to offer. Proxima Centauri is 4.24 light-years away. That distance will not shrink on its own. The star will not become gentler, or the interstellar medium less hazardous, or the timescales less daunting, simply because we wish it otherwise. The universe does not accommodate our impatience. It operates on its own schedule, at its own scale, according to its own rules, which it did not consult us about before implementing, but we are learning those rules. Piece by piece, observation by observation, equation by equation, experiment by experiment, generation by generation, we are mapping the shape of the impossible with enough precision that it is slowly, carefully, beginning to reveal where the possible might be hiding inside it. And that process, the mapping itself, the honest confrontation with difficulty, the refusal to stop asking even when the asking is hard, is one of the most genuinely beautiful things our species has ever done. The next time you step outside on a clear night, look towards Centaurus. You won't see Proxima, but you'll know it's there. Small and fierce and ancient, surrounded by its violent radiation and its candidate worlds and its unanswered questions, 4.24 light-years away in the direction you're facing, and somewhere in the space between you and that star, in the interstellar medium that is not empty and not safe and not waiting for us, the future of this question is being written by researchers and engineers and philosophers and students and curious people who don't yet know that they're curious, by the slow accumulation of knowledge that compounds across generations in ways no individual generation can fully see. We are made of stardust. We are the universe looking at itself and asking where the rest of it went, and the answer, incomplete, uncertain, radically open, and full of horror and wonder in equal measure, is out there, waiting the way all the best answers wait, for the right question to finally catch up with it. And if Proxima Centauri broke your brain a little, then you have to click the video on your screen right now. We explore why even warp drive won't save us from the distance between stars. Even if we somehow cracked faster than light travel tomorrow, the universe still has a few horrifying tricks up its sleeve. Trust me, you need to see this one.